Every developer who uses AI has hit the same wall. You start a project, feed the assistant your prompts, and by turn 25, it has lost the thread of your architecture. You end up spending more time fixing context errors than building features. Gemini Conductor fixes this memory loss. It operates as a central terminal hub, routing instructions to programming language nodes using tracks for persistent memory. Running in the command line, it saves project memory as standard Markdown files, making context portable across shells and teams. To begin, you only need two prerequisites: an authenticated Gemini CLI and a blank folder open in your code editor. By moving AI memory to the terminal and standardizing it in Markdown, you create a versioned context directory that lives directly alongside your source code. The first step is to initialize your workspace. Open your terminal and run the setup command. As the command executes, a new directory appears in your file tree, containing core files like product.md, techstack.md, and workflow.md. The techstack.md file then populates with your specific languages, frameworks, and SDKs, providing a permanent reference point. These configuration files establish a set of rules that the AI is required to follow for the entire lifespan of the project. Establishing this shared context removes the need to manually re-explain your goals and tech stack in every new AI prompt. Now we can scope a specific feature. We'll build a user authentication module by running new track. Conceptually, a track is a self-contained unit of work. It functions like a project management ticket that is readable by both humans and AI. As shown in this file tree, the command generates a new folder containing two critical artifacts: a spec.md for requirements, and a plan.md for the execution steps. This ensures the AI has a roadmap before it begins coding. To optimize the results, open the spec.md file and add negative constraints to the AI's instructions. A negative constraint explicitly tells the AI what not to do. For example, you might forbid the use of third-party authentication libraries, forcing the AI to use native cryptography instead. This works because research indicates that negative constraints often outperform positive instructions on creative and analytical tasks. Structuring the AI's workflow through a track ensures it follows a predictable sequence of specification and planning before a single line of code is written. Once you have approved the plan, execute the implementation by running the implement command. This starts the agentic loop. Like these interlocking gears, the AI reads your plan, inspects your codebase, and writes new code in a rapid cycle. You can see the progress in real time. Each empty bracket converts into a filled checkbox as the corresponding code is generated. Before marking a task complete, a validation pulse sweeps the code, running tests and verifying the output passes. If the output is incorrect, the /conductor revert command provides a Git-based safety net, allowing you to instantly undo a specific track. To see a high-level overview of all pending and completed features, use the /conductor status command. Because this state is saved in your local directory, you can close your machine and resume work later without losing any project context. Watching the AI execute its own plan shows how structured orchestration provides a clear, documented record of the implementation process. The final result of the track is a functional, production-ready module, generated following the specific architectural rules you established. We followed three fundamental phases: building a project-wide context directory, scoping a specific track, and executing the approved plan. The primary difference is that this entire process happens via CLI and Markdown, keeping the developer independent of specific IDE plugins or proprietary ecosystems. You can test this framework independence yourself. Use the links in the description to install the CLI and attempt to build a project using your most obscure programming language.